we have two linear equations involving the same two variables. If we take them and consider them together, we have what we call a system of equations. And we are interested in this videotape in solving such systems of equations involving two linear equations and two variables. Now, when I say solve a system of equations, let's say the two variables in the problem are x and y. When I solve a system of equations, I'm interested in finding all ordered pairs x comma y that satisfy both equations in the system. Okay, now we are aware of the fact that a linear equation in two variables, when you graph it, you always get a straight line. If we take two linear equations and two variables and graph them on the same set of axes, okay, where these two equations intersect, that would be the solution set for the system of equations. Okay, wherever the two equations intersect, any point where the two equations intersect would be a solution of the system of equations. Now, when you take two linear equations and two variables and graph them on the same set of coordinate axes, one of three things might happen. Okay, the first thing that might happen, and this is the most common occurrence, is that the two equations, which when you graph them you get two straight lines, intersect at one and only one point. Okay, there is only one point that is on both of these straight lines at the same time. Therefore, there is only one solution to the system of equations. Okay. One solution, a unique solution to the system of equations. This happens when the lines intersect at one point. The lines intersect at one point, indicating there is one solution. Remember, wherever the lines intersect, that indicates a solution of the system of equations. So if they intersect at one point, then there is one solution to the system of equations. Now, two other possibilities that might occur. Okay, these are a little rarer. One possibility, the two lines might be parallel to each other. They might never intersect. Okay, since the solution set would be the set of all points where the lines intersect, and they never intersect, there are no solutions to the system of equations. Okay, if the lines are parallel, it means they never intersect. There are no solutions to the system of equations. We say that the equations are inconsistent. We cannot solve them simultaneously. There are no points that are on both lines at the same time. The lines are parallel. There are no points of intersection. Okay. The third possibility is that we take first the equation and we sketch its graph and we get a certain straight line. And then we take the second equation and we sketch its graph and we get a straight line. And it turns out that that line falls right on top of the line that we have here. In other words, the two lines coincide. Okay? Both equations, when graphed, give you exactly the same line. In other words, you have different forms of the same, the equations are different forms of the same straight line. The lines coincide. In such a case, since both lines fall on top of each other, we have a situation that every point on the line, okay, every point on one line is also on the other line, and we have an infinite number of solutions. There are infinitely many points on the line, and any point on the line, of course, satisfies both equations, so we have an infinite number of solutions. In such a case, we say that the equations are dependent. Okay, so let's review the three possibilities. The two lines intersect at one point. There is therefore one solution to the system of equations. The two lines never intersect. They are parallel. There are no solutions to the system of equations. The equations are called inconsistent. And finally, the lines fall right on top of each other. They coincide. Any point on the line on one of them also satisfies the other equation. We therefore have an infinite number of solutions to the system, and the equations are called dependent. Okay, now we have three popular ways for finding the solution set for a system of two equations and two variables. One way is, of course, to graph the two equations. Okay, now if you graph the two equations, okay, let's say the possibility happens here that the two lines intersect. If you graph the two equations, if you can read off, if, for example, this turned out to be exactly at an integer, in other words, exactly at, you have these lines marked off, and you could see that this is 2 units over, 1, 2, 3 units up, and the solution was at 2, 3, well, fine. But most of the time, the solutions are not going to be exactly at whole numbers, and it's going to be very hard to read off the solution from a graph of any kind of accuracy. Of course, if you do graph them, and one advantage of the method of graphing, it's very easy to get, say, an approximate solution. Okay, you can get a quick idea about where the solution falls. Okay, but because of the inaccuracy in trying to read off the solution from the graph, we prefer algebraic methods of solution for systems of equation. And I'm going to be showing you two ways of solving such a system of equations. Let's look at a specific example. Okay, 5x plus 2y equals 9, one equation, in one linear equation in two variables. And let's consider another linear equation in the same two variables, 2x minus 3y equals minus 4. Taken together, we have a system of equations. We would like to solve the system of equations. Find the set of all points x comma y, or all ordered pairs x comma y, that satisfy both equations in this system. Okay, now the first method I'm going to be showing you is the method of elimination. In this method, what we do is we know we can multiply both sides of an equation by a non-zero constant and get an equivalent equation. What we'd like to do is to say, take the first equation, multiply both sides of the equation by some constant, take the second equation, multiply both sides of that equation by some other constant in such a way that when you add the two equations which result, one of the variables is eliminated. It drops out. This produces a third equation in just one unknown, which we solve. And once we have found that solution, we can substitute into either of the other two equations here to get the other variable. So we try to work it so that we've eliminated one variable from the system. Okay, now, let's see what we can do here. If we were to multiply, for example, both sides of the top equation by 3, and both sides of the bottom equation by 2, let's see what would happen. And then I'll explain why I just picked these numbers. The top equation would become 3 times 5x, which is 15x, okay, plus 3 times 2y, which is plus 6y, equals 27. The bottom equation would be 4x minus 6y equals minus 8. Don't forget this 2, we're multiplying both sides of the equation. Every term gets multiplied by the 2. So it becomes 4x minus 6y equals minus 8. Okay, now we have been successful here because when we add these two equations, look what happens. 15x and 4x gives us 19x, plus 6y and minus 6y gives us 0y, or 0, equals 27 minus 8, which is 19. We have produced an equation which involves only the variable x. In other words, y has been eliminated. This, of course, is very simple to solve. We divide both sides by 19 to get x equals 1. And once we know x equals 1, we can then substitute into either of the two equations that we started with, or any of the equations in the system involving both variables, okay, and figure out what y is. We would have 5x plus, say, 2y equals 9, letting x equals 1. 5 times 1 plus 2y equals 9. Subtracting 5 from both sides of the equation, 2y equals 4, y equals 2, dividing by 2. So we have x equals 1, y equals 2. And we're going to check that in a moment. Just want to go back over here and review what we did. I multiplied both sides of the top equation by 3, both sides of the bottom equation by 2. And in doing that, the coefficient of y here became plus 6, and here it became minus 6, so that when you added the two equations that resulted, the y's dropped out. Okay, so we're always interested in producing this kind of a system. Now, what we have done here is, say, basically use this coefficient, okay, without the minus sign up here, and this coefficient down here to produce the 6 and the minus 6. Okay, sometimes there are more efficient ways. You don't always have to use the numbers that are here in the reverse order. The trick is we'd like to produce two equations in which the absolute values of the coefficient are exactly the same in one of the variables, but they differ. They have different signs. One is plus a number, one is minus the same number. Okay. Now, another possibility in solving this system would have been to try to eliminate x. You could have multiplied both sides of the top equation by 2. That would have given you a 10x here, and multiplied both sides of the bottom equation by minus 5 to produce a minus 10x here. So then when you add the two equations, the x's would have dropped out. Okay, so you could have either eliminated x or eliminated y. That doesn't matter. Okay, having done that, we were able to solve. We had an equation in just one variable, which we could solve for that variable. Then you can choose any of the other equations that are lying around in both variables to figure out what the other variable, y in this case, is. Now, having done that, you should always go back to the original two equations that you started with and check your answers. Okay, we believe the solution is x equals 1, y equals 2. The first equation was 5x plus 2y equals 9. So 5 times 1 plus 2 times 2 should be equal to 9. 5 plus 4 should be equal to 9, and of course it is. The second equation was 2x minus 3y equals minus 4. Okay, once again, letting x equal 1 and y equal 2, we should get a true statement. 2 times 1 minus 3 times 2 should be equal to minus 4. 2 minus 6 should be equal to minus 4. And minus 4 equals minus 4. It checks out. Okay, so we have found the solution. If you were to graph these two lines, what you would have would be them intersecting at only one point. The point would be 1, 2. Let's consider another system of equations. What I would like to do is show you how the other possibilities, remember I said that most of the time the two lines intersect in one point. There's a unique solution to the system. But there are other possibilities. We know that the lines might be parallel, okay, in which case there are no solutions, or they might coincide, in which case there are an infinite number of solutions. I'd like to show you how these possibilities manifest themselves algebraically. You know what they look like geometrically, but how you'll recognize them if it happens when you're solving your systems by the method of elimination algebraically. Okay, consider the following example. X minus y equals 3. 2x minus 2y equals 6. Okay, we would like to solve the system by elimination. All right, let's multiply both sides of the top equation by minus 2. You get minus 2x plus 2y equals minus 6. And if you add that to the bottom equation, just leaving it alone, 2x minus 2y equals 6, you'll see an interesting thing happens. Not only have you eliminated, let's say your plan was to eliminate the y, not only have you eliminated the y, you've eliminated the x as well. You have 0x plus 0y, which is 0, equals, on the right-hand side, you get minus 6 plus 6, when you add them together, equals 0. So you have eliminated both variables. Are eliminated. And the resulting statement is a true statement. Both variables are eliminated, and the resulting statement, 0 equals 0, is, of course, a true statement. Therefore, the resulting statement is true. In this case, we have the lines are dependent. Okay, the equations are dependent. We have an infinite number of solutions to the system. These lines really coincide. If you look for a moment, you will notice if you had multiplied both sides of the original equation by 2, you would have gotten 2x minus 2y equals 6, which is precisely the same equation that you have here. These are both of these equations, if you graph them, would produce the following line. If you look at the top one, if y equals 0, looking for the x-intercept, if y equals 0, x equals 3. If x equals 0, y is equal to minus 3. That's the top equation. And the bottom equation, of course, if y equals 0, 2x equals 6, x equals 3. If x equals 0, y is equal to minus 3. Of course, it has the same x and y intercepts. It is the same line. So what we have here, and this shows itself algebraically, that both variables are eliminated when you try to use this method of elimination, and the resulting statement is true. Okay? This tells me that the equations are dependent, and there are an infinite number of solutions. Any point on this line is a solution to the system. Since if it's on this line, it satisfies obviously both of these equations. These are both equations of the same straight line. So for example, 3, 0, 0, minus 3, anything else that's on the line, okay, there are an infinite number of points on the line, would be a solution to the system of equations. Okay, let's consider another system of equations. 2x plus y equals 4, and 4x plus 2y equals 5. Okay, once again, I would like to solve this by the method of elimination. Let's say I try to eliminate the variable y. I could multiply both sides of the top equation by minus 2. This would give me minus 4x minus 2y equals minus 8. Okay, multiplying every term in the top equation by minus 2. Let's leave the bottom equation alone. 4x plus 2y equals 5. When you add the equations, both variables are eliminated. You get 0x plus 0y, which is 0, equals minus 8 plus 5, which is minus 3. Once again, both variables have been eliminated. But unlike the preceding problem, the resulting statement is false. The resulting statement is false. This indicates that the equations are inconsistent. You cannot solve them together. Okay, there are no points that satisfy both equations at the same time. Okay, so the equations are inconsistent, and the system has no solution. And if you try to graph these lines, let's graph the two equations that we have. The top one, just using, say, intercepts. When y is 0, x is equal to 2. When x is 0, y is equal to 4. This is a graph of the top equation. The bottom one, when y is 0, x is equal to 1 1/4. When x is 0, y is equal to 2 1/2. This line looks like this. It is parallel to the other line. Okay, the lines do not intersect. There are no solutions to the system of equations. Okay, so if you are able to solve simultaneously by the method of elimination, you get an x value and a y value, there's a unique solution to the system. If, however, when you're trying to eliminate one variable, both variables are eliminated, and the resulting statement is true, then the equations are dependent and there are an infinite number of solutions. If, however, when you try to eliminate one variable, both variables are eliminated and the resulting statement is false, for example, 0 equals minus 3, then we say the equations are inconsistent and there are no solutions to the system of equations. The top equation, let's say, is 4x minus 3y equals 11. The bottom is 7x plus 5y equals minus 4. I would like to solve this system of equations. Okay, let's say we start off by eliminating the variable x. Okay? To do that, I could multiply the top equation, both sides of the top equation, by, let's say, 7, and both sides of the bottom equation by minus 4. This is to produce a 28x here and a minus 28x here, which will cancel each other out. Let's go ahead and do this. 7 times 4x, that's 28x, minus 7 times 3y, that's minus 21y, equals 77, minus 28x, minus 20y, equals plus 16. Adding both equations, the x's drop out. We have here minus 41y equals 7 and 6 is 93. Therefore, y, dividing both sides by minus 41, y is minus 93 over 41. Okay, now, one thing that you could do now is to take y equals minus 93 over 41, substitute into either of these two equations that we started with, and solve for x. Okay, and you can do that, and it will work out. I want to mention another possibility, which in this example, of course, would be preferable, and that is, it would be easier actually to start the problem from the beginning, this time try to eliminate the variable y and solve for x that way, than to try to substitute in something, a fraction, okay, of this form. It's your choice, and you can substitute in this value for y in and solve for x. But I want you to consider you might try that on your own and see how it works out. It's easier to restart the problem and this time to eliminate the other variable, y. Let's try that. Starting it again, 4x minus 3y equals 11. 7x plus 5y equals minus 4. I want to eliminate the y this time, so let me multiply both sides of the top equation by 5 and both sides of the bottom equation by 3. Okay, I don't need to multiply by a negative because these coefficients already have opposite signs. So when I do this, I will get on the top equation 20x minus 15y equals 55. And the bottom equation, I'll get 3 times 7x, 21x, plus 15y equals minus 12. And I will add the equations. 20x and 21x gives us 41x. The y's drop out. We have 0y equals 43. 55 minus 12. Dividing both sides of the equation by 41, we get x is equal to 43 over 41. Okay, the advantage here is that I did not have to substitute something like y equals minus 93 over 41 into the equation and work with crummy fractions to solve for the other variable. Okay, by just going through the entire procedure again, in this particular case, it was easier, I think, to get the other variable. Okay, of course, if you got a fairly nice answer for this variable, then you would want to substitute it in. But if it is a crummy fraction, feel free to go back to the beginning and eliminate the other variable. And of course, you could check this by substituting in, but I don't want to. You'll have to take my word on it this time. We've discussed two ways of solving two methods of solving a system of equations. Graphic method, in other words, just graphing the two equations and looking, for the solution that way, but it's not too accurate. The method of elimination, which we have gone through, and we understand how we would recognize, say, a unique solution, infinite number of solutions, or no solution to the system. And one other possibility, I would like to show you now the method of substitution. For times where this is applicable, it can be easier than the method of elimination to use. It's not always applicable. But when you can use it, sometimes this produces a solution quicker than the method of elimination. Let's say you had a system of equations like this. 3x minus 2y equals 4. And x minus y equals 1. Okay, now we are aware of the fact that we could solve this system by multiplying, say, both sides of the bottom equation by either a minus 2 or a minus 3 and then add to eliminate one of the variables and go through that procedure. What makes this system special is that it's particularly easy to solve either for x or y. Okay, if let's say you wanted to solve for y in this equation, you would have adding y to both sides, subtracting 1 from both sides, you'd have y equals x minus 1. Okay, what makes it particularly interesting is that it's, the coefficients of x or y are equal to plus or minus 1. So it's particularly easy to solve for either y or x. Or we could have said x is equal to 1 plus y, or y equals x minus 1. We replace this equation by this one. Now, in this equation, we already know what y is in terms of x. We can then substitute this value for y in the original equation. That is going to have the effect of eliminating y from that equation, and you can go directly into solving the top equation in one variable. Let's look. We have 3x minus 2y equals 4. But y, from the second equation, we can see readily, y is equal to x minus 1. So we say 3x minus 2 times y equals 4, but let me write down for y what it's equal to in the second equation, namely x minus 1. 3x, now distributing the minus 2, minus 2x plus 2 equals 4. X, 3x minus 2x combining like terms, x plus 2 equals 4. Subtracting 2 from both sides, x equals 2. Okay, since x equals 2, we can substitute into, say, the second equation here, y equals x minus 1. So if x is equal to 2, y must be 2 minus 1, or 1. X equals 2, y equals 1 is the solution to the system. Okay, we see that 1 is equal to 2 minus 1. It obviously works here, or 2 minus 1 equals 1. That's the equivalent equation. Now here, 3x minus 2y equals 4. 3 times x, that's 3 times 2, 6. Minus 2 times 1, 6 minus 2 equals 4. So it checks out. Okay, so if you are given a system of equations where either the equation, one of the equations is solved already for one variable, or it looks to you very simple to solve for one variable, okay, you could then substitute that value for the variable into the other equation, get an equation in only one variable, solve that, find out the other variable, and you've solved the system of equations. Okay, and that brings us to the end of this videotape.